Request Mr. Jayaraman to mute.
Yes, sir.
Yes, Professor Kirti.
A very good afternoon to all of you and to Professor Lee. On behalf of Global Center of Excellence in Affordable and Clean Energy, GCOE ACE at IIT Dharwad, I, Dr. Kirti MC, faculty member of the Department of Mechanical Materials and Aerospace Engineering, IIT Dharwad, extend a very warm welcome to this technical talk, a part of the talk series called TREES, which stands for Talks on Renewables, Empowering Earth and Sustainability, brought to you by GCOE ACE at IIT Dharwad. I heartily welcome the speaker, Professor Poh Seng Lee, who is the Executive Director of the Energy Studies Institute, ESI, Director of Singapore Energy Center, SgEC, Director of Center for Energy Research and Technology, CERT, and Program Director of Cooling Energy Science and Technology, Singapore, CoolestSG, which is a national consortium at the National University of Singapore in US. Before I formally introduce the speaker, I request Professor Dheeraj Patil, faculty member in the Department of Mechanical Materials and Aerospace Engineering, IIT Dharwad, to welcome the guest and to introduce the Global Center of Excellence in Affordable and Clean Energy, GCOE ACE at IIT Dharwad. Professor Dheeraj.
Yeah, my screen is visible. Right?
Yeah.
Okay, I briefly introduce you to this center. This is a Global Center of Excellence in Affordable and Clean Energy. We abbreviate it as GCOE ACE. The center is committed to provide laboratory facilities, the upskilling for the youth, the research and development primarily in the combustion research and in the power electronics, the outreach activities and the talk series, which we named as TREES, hackathon and challenges, innovation support and incubation support, as well as grassroots implementation, field level experiences, field deployments, and field mentorship. The center is in partnership with Honeywell, the Principal Scientific Advisor of Government of India, and Selco Foundation. The center is working towards the Sustainable Development Goals given by United Nations, and this Sustainable Development Goal number 7 is the affordable and clean energy, which is linked to the other Sustainable Development Goals. The current status of the center is in the establishment of the lab equipment. We have lab equipment in the test and measurement, fabrication laboratory and prototyping laboratory, skill development laboratory, and R&D in power electronics. We are in the process of making a field test lab, which we call as Modern Clean Energy Village in the nearby village near to the IIT Dharwad. The center is inaugurated on 20th January 2022 by PSA Professor K. Vijayaraghavan, and also brings you the outreach activity, which we call as TREES, Talks on Renewables, Empowering Earth and Sustainability. These were previous speakers in this series, and then they spoke about various aspects, primarily poverty and technology, sustainability, biofuel policy, as well as nanomaterial, functional nanomaterials, wind energy, digitalization, and ocean energy. Today's talk is by Professor Lee. I welcome Professor Lee for the talk number 6 in this series. This talk is on high performance cooling techniques for decarbonization of data centers. One of the part of the outreach activity that we are now conducting is inviting a problem statements. Basically, we are looking for problem statements from grassroots level people who have been impacted due to the lack of access to the reliable energy source and might be adversely impacting the livelihood, health, and education of anyone in your community. So there is this link. There is a you can scan the barcode and you can get the application form. So I invite participants to participate in this problem statement identification. Thank you for joining this talk. I hand over to Professor Kirti.
Thank you, Professor Dheeraj. Now it is my immense pleasure to introduce the chief guest before inviting him to begin the talk titled High Performance Cooling Techniques for Decarbonisation of Data Centers. Professor P.S. Lee is an associate professor in the Department of Mechanical Engineering at the National University of Singapore, who specializes in heat transfer. In addition, Professor Lee is the founder of CoolestDC, a startup focusing on development and delivering high-efficiency liquid and two-phase cooling solutions for the data centers. He is a fellow of the American Society of Mechanical Engineers, ASME, the Energy Institute, EI, and the Institution of Engineers, Singapore, IES. His research group focuses on the fundamental study and enhancement techniques, including design, numerical simulations, and experimental investigations for microchannel heat transfer and its applications in various thermal systems. It comprises of four main thrusts: fundamental understandings of microchannel fluid flow and heat transfer step enhancement of single-phase liquid flow in microchannels, phase flow in microchannels, and enhanced thermal systems. His group is actively addressing data center cooling, electric vehicle battery thermal management, and power electronics cooling applications. Dr. Lee has co-authored more than 150 peer-reviewed papers, including journals and conferences, and 3 books. His research work has been cited 7,709 times with an H index of 41. I now invite Professor Lee to begin his talk, and I also request him to please share the screen.
Okay, thank you, Dr. Kitty. Let me share my slides.
And I would like to inform the audience that you may post your questions in the question and answer box that is available in the corner here. So you can go to activities in the corner and then click on Q&A. Back to you, Professor Lee.
Okay, sure. Can you see my screen?
Yes, Professor.
Okay, a very big thank you for inviting me to deliver this guest lecture. So the title of my presentation is High Performance Cooling Techniques for Decarbonization of the Data Centers. Okay,
Professor, you may click on the hide button there so that you can see the
button. Oh, okay.
Yeah,
sure. Okay.
Thank you.
So before I start, I would like to introduce my research group here at the Department of Mechanical Engineering at the National University of Singapore. So my group currently have about 17 research members, comprising of mainly research staff and 4 PhD students. So some of the hardwares that my group have includes like the flow loops for conducting experimental investigation on liquid and two-phase cooling studies, as well as compact and desktop wind tunnels for the investigation of air cooling studies. There's also a micro PIV and micro LIF, which stands for laser-induced fluorescence systems, which allows us to conduct flow and temperature fuse measurement in microfluidic devices. Yeah, so on the right are some photographs that show some of the hardware that we have in our labs. So in terms of other research resources listed here, so we have like high-speed cameras, which allows us to conduct the flow visualization studies for flow boiling in microchannels. Then there's high-speed data acquisition systems, 3-axis measurement microscope, as we do a lot of works pertaining to microchannels, as well as research-grade IR cameras. So in terms of the softwares, we rely quite heavily on our NUS super visualization unit cluster, which are basically our kind of like supercomputing facilities. There's also quite a number of in-house workstations, as well as CFD packages for us to conduct the CFD analysis. Okay, so again, on the right, there are some pictures showing some of the research hardware. Okay, so today we'll be actually covering 4 sections. I'll start by introducing the acceleration of digital transformation. right, which actually leads to the increase in compute intensive workloads. Second, I will describe the current data center trends. In particular, the growth of the data center industry is associated energy consumption and carbon emission. Then I will briefly introduce the different pathways for decarbonization of the data center and specifically converging towards liquid cooling solutions. And for the fourth part, I will describe some of the ongoing work within my research group, as well as being carried out by CoolestDC, my startup company, on high performance liquid cooling for effective co-management cooling power of data centers. Okay, so if you look at the global scales, so the COVID-19 crisis has actually accelerated the transformation towards the digital economy, right? So nowadays we do a lot of virtual conferences, including the Zoom as well as MS Teams meetings. So as well as do a lot of online shopping. But at the back end of all these digital activities are still physical hardware, especially the servers that's residing inside the data centers. So if you look at the share across the different regions, right, in terms of the adoption, the accelerations, right? So clearly there is actually the accelerated, right? But when you look at the July 2020, so pretty much across all the different regions, right, including APAC, Europe, and North America. So it actually experienced a spike in terms of the adoption rate, right? So clearly this is in quite a big contrast compared to pre-pandemics the development. And globally, and likewise, we're actually expecting a 55% increase in terms of the adoption accelerations. So the acceleration of digitizations and IT advancement actually drive the rise in the demand for the compute intensive workload tools, right? Because associated with the development of the latest chips, right? So you're going to pack a lot more of performance as well as functionalities into increasingly the small footprint. So the net result is actually the rack density or the server rack density is actually going to increase by quite a bit, right? So if you look at the figure on the left, which shows the density in terms of the kilowatt per rack, right? So from 2016, the average density, the raw rack density is actually about 5.1 kilowatt. But by year 2020, it's actually the 8.4. So that's actually quite a substantial increase in terms of the rack density. So increasingly, we are finding that air cooling is actually reaching its physical limit. So in order to effectively manage the temperature as well as the IT power consumption, so a lot of attention has been sort of put on the liquid cooling. So there are some of the reasons or examples on the rapidly developing technologies that are actually driving the demand for this increase in the IT workloads, so which is listed here. But some of the common applications or technologies are shown, right? So like the cloud services, virtualization and containerization, AI and machine learning, which actually requires, for example, very high GPU compute power. Then there's IoT, blockchain, 5G networks, as well as edge computing. So all in all these rapidly developing technologies actually leads to the increase in terms of the compute intensive workload. So if you look at the associated growth in the data center industry, which is actually summarized by this report by Cushman and Wakefield. So if you focus on the APAC region, you'll find that in terms of the compound annual growth rate, it's actually in fact expected to be higher by the year 2024 at 12.2%. And the associated market size is actually US 28 billion. And this is even greater compared to the market size for North America, right? Because the compound annual growth for North America is actually much lower at 6.4%. And if you further zoom into Southeast Asia, where Singapore is actually located, right? So Southeast Asia is actually seen as the faster growing region for co-location data centers for the next 5 years. So I think those reasons or the emerging technology that we mentioned in the previous slide will very much applies to this part of the world, right? So if you look at the compound annual growth rate, it's actually even higher than the average for APAC, so standing at 12.9%, and the market size is expected to reach 3.5 billion by year 2024. But associated with the growth with the data center industry, there's also the associated power consumption, water consumption, as well as the carbon emissions. So there are three key factors which will actually affect the carbon footprint of the data centers, right? So first is actually the location. So why location is important is because the physical location of data centers will then be subjected to the local climatic conditions. So for example, operating data centers here in the tropics, right, is actually the more energy sapping, right, because of a high ambient temperature and humidity. So in order to sort of manage or control the data center environment at an acceptable level that will ensure the IT reliability as well as the IT, the so-called longevity. So you need to consume quite a bit of energy in order to manage the temperature and the humidity. Second is actually the IT load, as we discussed earlier on. So associated with the increase in consumption of the digital services, right, as well as the associated digital economy. So it's going to lead to increase in terms of the IT load. So certainly as IT load increases, that will also lead to increased energy consumption and the associated carbon footprint. The third is actually energy efficiency. So if you look at the trends for the power consumptions for data centers, actually interestingly, it has not increased as much as the consumption or the increase in terms of the digital services, right? Because over the years, there have been a lot of efforts put into raising the energy efficiency for data centers. But even so, I think we are fast seeing, for example, as what we discussed earlier, for example, the conventional air cooling actually approaching its physical limits. That's why there's actually an urgency for us to develop more efficient cooling solution in order to manage not only the temperature of data centers, but also the associated IT power consumption and performance, which I will be explaining in the next few slides. Right. Then the other aspect of data center is actually the depth of water consumptions, right? Because especially in this part of the world, because of the challenging climatic conditions, so a lot of water is actually consumed, basically operating what we call wet cooling towers. Right? So all this will affect, is directly affected by the operation of the data center. Then the other aspect that increasingly people are looking at is actually that of embodied carbon, right? So for example, the construction materials used for the data centers, which is not the focus of this presentation. So for this presentation, I'll be focusing more on the operational carbon emissions for data centers. So I already briefly alluded to the associated carbon footprint, right, due to the large amount of energy consumed by data centers. So this slide actually provides a little bit more detail. So according to the international energy agencies, data centers is currently accounting for 200 terawatts hour per year in terms of the energy consumption, which is about 1% or 1 to close to 2% of the total electricity demand worldwide. And the associated carbon footprint is actually provided in this figure on your right, so which is really quite a scary number. And if you look at on the left, it actually shows the breakdown in terms of the types of data centers, ranging from hyperscalers to the cloud to traditional colo operators. Right? So for hyperscalers, this includes the like of AWS, Amazon Web Services, the Microsoft, Google, or Facebook. Right? So for hyperscalers, they are already implementing a lot of energy efficient initiative. Right? For example, some of them are really going into immersion coolings or whatnot, and likewise for some of the cloud operators. But what is most challenging is actually for the co-location data centers, right? Because for co-location data centers, you have to basically handle the multi-tenants. So it's not that easy to get all your tenants to agree to, for example, switching to liquid cooling. Yeah. So currently for CoolestDC, we were actively working with some of the major colo operators in order to get them to significantly reduce the carbon footprint. So I will like to present this next slide that provides a summary of the different pathways that would result in the decarbonizing of data centers. So we'll start with, for example, looking at the solar energy. So I think besides the initiative related to energy efficiency, there's also a lot of interest in terms of integrating green energy sources to data centers, right? So then solar energies, or if relevant, other types of renewable energy are actually actively being looked at, right? So solar energy is actually becoming increasingly available for data center operators to tap into, especially I think a lot of data center operators are also purchasing renewable energy credits, right, in order to offset the carbon emissions that are generated by their data center operations. The other topic that has generated a lot of interest in the last 1-2 years is hydrogen. Right? So hydrogen actually represents a cleaner alternative fuel, especially for data center backup power. So we are actually actively in discussion with major colo operators to look into the possibility of doing a hydrogen fuel cell demonstration here in the NUS campus. So the most obvious pathway is actually the energy efficient cooling technologies for this very simple reason, right? So up to 35 to 40% of the energy the usage is actually generated for meeting the cooling needs. And associated with more efficient cooling technologies such as liquid cooling, this can actually result in very substantial reduction in the carbon footprint. So that will be the focus of my presentation today. But I will quickly run through other pathways. For example, we can also look into recovering free coal energy from the regasification of the LNG, right? So especially in the context of Singapore, we actually import quite a bit of liquefied natural gas. But before the natural gas can be sent through the pipeline, we have to actually regasify it, because the LNG actually is transported to Singapore in the liquefied forms, right? So that they can be stored more effectively in the LNG, the so-called tankers, right? But before it can be sent through the pipelines, it has to be gasified. So in the process, it actually releases a lot of free coal energy, right? So if you can actually recover this coal energy and use it for cooling data centers, that also make it more sustainable, right? Instead of actually we consuming electricity from the grid, right? The other is actually whether or not we can, instead of discharging the waste heat to the ambient, we can actually, for example, discharge the waste heat to seawater, right? But there are some associated challenges, but this is certainly an option that we are also actively looking at. The other is actually to locate the data center underground, right? So that it's actually less subjected to, for example, solar heat, thereby sort of allowing also taking full advantage of the lower temperature underground, right? So this is another area. If let's suppose you have the appropriate geographical kind of conditions, so we can actually look into locating data center underground. The other aspect is actually related to the modernizing of IT infrastructures, right? So because when you look at, for example, the PUE, power usage effectiveness of data center, it's not just related to the cooling, right? But it's also related to, for example, the UPS losses. So that's why there's also interest to look into using the lithium or zinc-based battery, right? Thereby actually trying to sort of reduce the amount of UPS losses. Then last but not least will be actually AI machine learning, right? So I think while we can actually have very high performance cooling solutions, with the use of AI machine learning, that can actually allow us to optimize the operation of the cooling systems, right? Or you can actually look into using AI machine learning to look into distributing the IT workload, right? Thereby actually making your data centers as efficient as possible. So next, I'd like to show you a chart that was actually presented by the recent Uptime Institute report on data center cooling system, right? Or specifically known as a data center cooling system survey, right? Which was actually issued, I think, in Q3 of 2021, right? So if you look at this particular chart, it actually shows that the few think that air cooling will remain dominant beyond 10 years, right? So for example, if you look at between 1 to 3 years, only about 13% of the surveyed participants actually thinks that the air cooling will actually remain dominant beyond 10 years, right? But most of them actually will think that for within 4 to 6 years, air cooling will no longer remain the dominant, right? Because of, again, as mentioned, due to the latest chip development, right? So increasingly, the data center operators are actually looking at using more efficient or higher performance cooling techniques. So if you look at the market size for data center liquid cooling, so based on this report by the GM Insights in 2020, so it's actually projected to reach $1.5 billion US dollars, right, in 2020, and up to 20% compound annual growth rate. So certainly there's actually a lot of potential for data center the liquid cooling solutions. And the market size is actually expected to double to USD 3 billion. Okay? And that's according to the estimate by Vertiv, one of the leading data center cooling equipment vendors. And if you look at the comparisons of the different cooling technique as a function of rack density, I think what is clear is actually when your rack density actually starts to exceed, for example, the 12 kilowatt per rack, right? So we have to start to look at more effective and higher performance cooling solutions, right? So in particular, I'd like to point your attention to these three techniques, right? Rear door cooling, which is also known as rear door heat exchanger, is basically involving piping the liquid all the way to the rear of the rack, whereby you do a localized heat exchange. So in doing so, you can ensure more uniform airflow distribution across the rack, thereby actually allowing you to manage the heat coming from the different servers that's actually located or installed inside the rack. The second is actually direct chip liquid cooling, which my research group and CoolestDC are actively working on. So this can easily handle rack density in excess of 25 kilowatt. And if you go even a step higher, I think there are also a lot of interest to look into immersion cooling, right? So again, as mentioned, due to the rising rack densities, right? So it actually means that higher performance cooling is actually necessary. Okay. So the other advantage associated with liquid cooling is it actually allows you to go chiller free. So to explain why this is the case, let me actually refer you to this chart on the left, which was actually taken from one of the presentation at the OCP, the Global Summit, about 2 years ago. I think it was actually presented by the Microsoft team, right? So the vertical axis is actually the server power consumption, right? The horizontal axis is actually the server inlet condition, right? Associated with liquid cooling and air cooling, right? So air cooling is actually the two bar to the right, right? Whereas for liquid cooling are actually the 3 bars on the left. So if you look at the air cooling, let's use 25 degrees inlet air cooling as a baseline, right? So if you were to actually increase the supply or the inlet temperature for air cooling from 25 degrees to 35 degrees Celsius, you notice that it will actually have a server power consumption penalty, right? Because associated with operating your chip at elevated temperature, right? It can actually has a power penalty because your chip actually operate less efficiently at elevated temperature. But if you look at liquid cooling, right? Let's look at the lowest inlet liquid temperature of 25 degrees, right? So if you compare this to the baseline of 25 degrees air cooling, so there's actually a very substantial reduction in terms of your server power consumption. So meaning that switching from air cooling to liquid cooling is going to give you, for example, the 30% reduction in terms of your server power consumption. But what is more interesting is actually as you increase the supply temperature for liquid cooling, right, going from 24 to 39 to 47, you'll notice that the server power consumption actually stays more or less constant. So what is the implication? Because the implication is for liquid cooling, you can actually operate without any chiller, right? Because the conventional way of actually performing liquid cooling is actually shown on the top right figure, right? Which actually requires coupling it with a chiller system, right? As shown over here, right? So in doing so, the supply or the server inlet temperature obviously will be actually low, right? For example, at 24 degrees Celsius. But the downside is actually obviously you need to have a chiller system, right? Which is going to take up space as well as going to actually consume additional energy. But if you look at the figure on your left, right, it shows that going from 24 to 39 to 47, right, the server power consumption basically stays flatline. So the implication is actually you can throw away with the chiller, right? Meaning that there's no need for you to use a chiller to condition your inlet temperature, right? You can actually allow your inlet temperature to be a few degrees above your outdoor temperature, which is actually illustrated by the figure below, right? So basically you can actually have your liquid cooling that is actually directly coupled to the cooling tower or dry cooler, right, through the use of a heat exchanger, right? And in doing so, you'll be able to operate chillerless data center liquid cooling systems. So the implication is actually there's no need for you to cater for chiller. There's no need for you to set aside the space for chiller. So it's actually going to not only reduce your capital expenditure, your capex, but it's also going to actually reduce your opex very significantly, right? Because again, with a chillerless operation, there's no need for you to operate chiller, right? Thereby actually allowing you to achieve very significant savings in terms of capex, opex, as well as the total cost of ownership. But liquid cooling also have this wonderful side benefit of actually significant improvement in your IT or your chip performance, improvement in your chip or IT performance. So let's look at the figure below. Again, this is actually taken from the presentation by the Microsoft team at OCP Global Summit back in year 2020. Right, so if you look at the baseline, which let's again use the 25 degrees inlet air cooling as the baseline, right? So you can see that the average GPU performance is actually about this level, right? So if you were to actually switch to or rather you were to increase the inlet temperature for air cooling from 25 degrees to 35 degrees, right? You see that there's actually a penalty in terms of the GPU performance, right? Because now the GPU performance is actually lower by about, for example, 15-20%. Okay, but if you were to switch from 25 degrees C air cooling to 24 degrees liquid cooling, right? You notice there's a big improvement in terms of your GPU performance, right? By as much as 80%, right? This shows that associated with the better management of your chip temperature, right? Your chip is going to operate very efficiently, right? And that actually translates to a much improvement in terms of your chip performance, right? And if you were to increase your inlet temperature for liquid cooling from 24 to 39, then you see that there will be a drop in terms of the GPU performance, right? So from this level to this level, but it's still actually higher compared to the 25 degrees air cooling case or baseline, right? And likewise, if you were to further increase the inlet temperature for liquid cooling from 39 to 47 degrees Celsius, you find that again, there's actually a slight drop in terms of your average GPU performance. But compared to the baseline, which is 25 degrees air cooling, right? You see that these are actually these two are actually comparable, right? So I think the message basically associated with liquid cooling, right? I think we need to look at not just, for example, the savings in terms of the cooling system, but also the associated impact on the IT power consumption as well as the chip performance. So my group have actually been working on enhanced fin structure for the past 15 years. Let me actually introduce one of the novel fin structure that we invented, right? It's actually known as the oblique fin. So I suppose most of the so-called audience would have some basic knowledge related to heat transfer. So I'll actually go through it fairly quickly, right? So if you remember from the undergraduate heat transfer course, right? So we know that the local heat transfer coefficient, right, as denoted by H, right, actually at the inlets to the channel, right, it actually starts at a very high value, because that's where your boundary layer is actually the thinnest, right? But as the fluid goes down the stream, right, or goes through the channels, right, the heat transfer coefficient will actually drop very sharply, right, due to the thickening of the boundary layer. And eventually, when the boundary layers actually merges at the center of the channels, then you'll find that your heat transfer coefficient basically stays at the constant, what we call the fully developed state, right? And this is what happens for conventional microchannels. So ideally, we want the local heat transfer coefficient, right, to stay as high as possible, meaning that it wouldn't actually experience such a big drop in terms of your local heat transfer coefficient as the flow travel downstream, right? So that's why if we can figure out a mechanism that would actually disrupt the boundary layer development, right, or allowing the boundary layer to periodically redevelop, that would then translate to improvement in terms of the local heat transfer or the local heat transfer coefficient, right? So the challenge is then how do we figure out a way to maintain the thin thermal boundary layer, right, along the entire length of the microchannels. Okay, and if you are able to do that, as mentioned, that would then translate to a much improvement in terms of your overall or the average heat transfer performance. Okay, so what we did is actually quite simple. So if you look at the figure on the left, it's actually showing a conventional microchannel. So what you're looking at is actually the top view. So basically, you have a parallel arrays of microchannels that are divided or separated by continuous straight fins, right? So the flow is actually the flow going from the right to the left, okay? Because the inlet is actually on the right and the outlet is actually on the left. And as mentioned, these are actually continuous straight fins. So what it is actually, we introduce oblique cuts along the flow direction. So in doing so, we actually allows the flow to actually undergo what we call flow bifurcation, right? Because if you look at let me maybe zoom into some of the details, right? So with the creation of the oblique cuts, right, you'll find that you're actually connecting an upstream point to a downstream point, right, for the adjacent channel. And we know that obviously an upstream point actually has a higher pressure compared to the downstream point. So you basically create a very small pressure difference, a small pressure drop, right, across the oblique channel or the oblique branch. And this is actually able to divert a part of the flow, right, to go from this main channel to these secondary channels, right, and which then rejoins into this adjacent channel. So in doing so, it actually leads to the redevelopment of the thermal boundary layer, right? Because in the conventional microchannels, obviously the thermal boundary layer is going to thicken, right, as the flow travel downstream. But now, because of the creation of such oblique channels, it actually cause the fluid to actually undergo this periodic regeneration of the thermal boundary layer. And in doing so, it actually mixes the fluid better, thereby actually enhancing the convective heat transfer. Okay, so we start by actually doing some simulation, CFD simulation. I'm just showing you a quick schematic. So for a microchannel fin pair, right? Because we can actually impose the periodic boundary condition. So the associated governing equations are actually listed here, which is the usual suspect, right? Your continuity equation, your momentum equation, the energy equations, right? Both for the liquid as well as the solid. Okay. And from the CFD simulation, it actually shows some interesting data. I'm just showing you the temperature contour. Okay. So if you look at the conventional microchannel, which is actually shown on the left, right? So there's actually the significant temperature difference from the microchannel wall, which is actually shown here in red color, right? To the fluid core, right? Which is actually having this blue color. So the fluid is actually not well mixed, right? Because we know that for microchannels, because of the low Reynolds number, so typically the flow is actually laminar, and that is actually not good for heat transfer, right? As we all know. But at the same time, you don't want to operate the flow in the turbulence regime for microchannel, right? Because otherwise you actually impose a very high pressure drop penalty. So for the oblique fin structure, it's actually quite interesting, right? So if you look at the temperature contour, right, it's actually definitely a lot more uniform compared to the case of conventional microchannel, right? Because you see that the color is actually relatively more uniform compared to that of conventional microchannel. That's actually showing quite a big temperature variation, right? Going from the red color, which is a higher temperature region, to this dark blue color region, which is actually the lower temperature core region. Whereas for the case of oblique fin, I see that the color is actually color coding, right? Definitely is actually a lot more uniform. Okay, and this is actually due to the better fluid mixing as we discussed, right? Because now you're getting part of the flow to branch, right, into this secondary channel, right? And in doing so, it disrupts the thermal boundary layer development, right? So in the case of conventional microchannel, as we discussed, right? So the thermal boundary layer will actually thicken as the flow travel downstream. And once the boundary layer actually merge at the center of the core, then you actually attain the fully developed state, right? Whereas for the case of the oblique fin array, right? Because you have sectional oblique fin, so whenever it hits a oblique fin, basically it actually induces a flow to basically go through this redevelopment effects, right? Thereby actually causing the thermal boundary layer to be periodically regenerated, right? Whenever it hits in oblique fin, right? So the net result is actually you get a lot more uniform temperature within the fluid region, right? And associated with that, you will have a much lower channel wall temperature, right? Because once the fluid is actually more well mixed, that means that it's able to convect the heat from the channel wall a lot more effectively. So in doing so, your channel wall temperature will be actually much lower, as actually shown over here. So the other thing that we've done is actually to extend these techniques to two-phase cooling. So you may be wondering how come I'm not showing you the single-phase results. I will be actually doing that in a later slide when we show the benchmarking with different fin structure. But I thought actually it would be sort of good to also introduce our work related to oblique fin two-phase cooling, right? So some of the results that we obtained is actually shown in this particular slide. On the figure on the extreme left actually shows the two-phase heat transfer coefficient, right, for the vertical axis, and the horizontal axis actually the effective heat flux, right? So if you look at the comparison between the straight fins, which is the continuous fins case, versus the oblique sectional fins, right, you find that the two-phase heat transfer coefficient that we are able to achieve are much higher compared to that of the single-phase, rather the straight fin case. The other things that is actually obvious actually in terms of the maximum heat flux that we are able to achieve, right, is easily about 2 to 3 times higher than the case of straight fins. So the implications, we are then able to extend the working range for two-phase cooling, right, once we deploy the oblique sectional fins. So the other thing that we have actually captured is actually the critical heat flux as shown in this middle figure, right? So if you compare again the performance of the oblique sectional fins versus the continuous straight fins, you'll find that the oblique sectional fins is able to achieve a critical heat flux that's easily 3 times that of your continuous straight fins. So again, actually attesting to the effectiveness of this technique when extended to the two-phase cooling region. And if you look at the associated wall temperature, right? So the figure on the top are actually pertaining to the straight continuous fins case. So you see that there's actually a certain temperature variation, and it's definitely higher, right? For example, ranging from 80-ish to about 100-ish. But you look at the case of our oblique sectional fins, right? So not only the temperatures are much lower at between 65 to about 73, they are also a lot more uniform, right? You can see that the gradient is actually a lot flatter compared to this linearly increasing trend associated with the straight fins, right? So showing that with the enhancement in terms of the two-phase the heat transfer, right, that actually translates to a very uniform performance as well as a much elevated efficiency. So we have actually conducted the high-speed visualization to better understand So what's happening when extending the oblique fin into two-phase cooling, right? For single phase, it's easy. We can just conduct CFD analysis, look at, for example, the temperature contour, the velocity contour, right? And you can see that there's this thinning of the thermal. It's actually more challenging because as it is right now, right? So I think the CFD or the numerical simulation of two-phase flow at heat transfer is still not that well established, right? So that's why we actually rely on the use of high-speed visualization, right? So we compare the high-speed visualization for the case of oblique sectional fins versus the continuous straight fins. So what is actually interesting is actually we notice that for the case of the oblique sectional fins, we are able to maintain a thin liquid film all around each of the oblique fins, right? So in doing so, it actually makes the boiling, flow boiling behavior very stable as well as very efficient. Whereas for the case of the continuous straight fins, right, you find that the liquid film thickness is actually much thicker, right? Meaning that in terms of effectiveness, it will definitely be of lower performance compared to the case of the sectional oblique fins. Then I think the last fin structure, which I'll probably just run through very quickly, is actually through the use of topology optimization. I think what I've described earlier on, you need to actually have some ideas as to what kind of fin structure or fin design that you want to, for example, either conduct CFD studies or to fabricate prototypes for testing, right? So in a way, you are constrained by the design, right? First, you need to actually have some idea as to what kind of design you want to investigate. Whereas for the case of topology optimization, is what we call like free-form optimization, right? So you can actually allow the simulation to freely morph to achieve a design that's actually the optimal, right? In terms of meeting certain objective function, for example, in terms of the lowest junction temperature versus pumping power. And that's what we did, right? So I won't go into details, but if you're interested, certainly I can sort of send you the list of our publication. So what we have noticed actually through the use of topology optimization, we are able to actually arrive at certain fin array patterns, right? That is kind of repetitive, and sort of using such repetitive fin patterns, right? We actually constructed another new design that's actually easily manufacturable. Yeah, let me just quickly show you some of the results. As mentioned, right? So we actually run a lot of runs using topology optimization, and referring to the result, right? We then actually simplify it, right, into certain repeating fin patterns, right, which can be manufactured more readily, right? So and we notice this particular fin structure, which we call the oblique trapezoidal fin array, which is actually very effective, right? If you remember earlier, when I described the oblique fin work, right, we said that the key mechanism is through the flow bifurcation, right? So because of this small delta P that we are actually creating due to the oblique channels, so we actually get the boundary layer to periodically regenerate, right? So that's shown to be very effective. But with the oblique trapezoidal fin array, we notice that in addition to the periodic generation of the boundary layers, right? If we were to actually allow the flow to actually go through a wavy kind of waviness, or you are able to inject some waviness into your fin array, that can actually in fact improve the performance further. So we actually did the quite detailed benchmarking, which is shown at the figure at the bottom left, right? It actually compares, for example, what I call this is a new fin design, which is basically the oblique trapezoidal fin array design. OV is actually an oblique fin design, right? Then there's a pin fin that is the offsets the straight fins. Then there's actually the straight fins, which are continuous fins, right? So if you look at the comparison of the junction temperature versus pumping power, so this new fin design, which is the oblique trapezoidal fin array, is actually the one that's closest to the origin. So meaning that you're able to get concurrently the highest performance, right, which is actually measured in terms of the lowest junction temperature, concurrent with the highest energy efficiency, right, which is actually measured by the lowest possible pumping power. So showing that this fin structure is actually really the excellent candidates, right, in terms of achieving not only high performance but also high energy efficiency. Yeah. Okay, And we actually did quite a bit of benchmarking. So again, this figure shows what I've described earlier on, but for a more zoom-in view, right? So again, you look at two of the fin structure that we have invented, right? The oblique fin and the oblique trapezoidal fin array. So again, we are able to achieve not only the lowest junction temperature, but also the lowest pumping power, right? Thereby allowing you to not only achieve very high performance, but also very, very high efficiency. And to realize that, right, so we have to make use of advanced manufacturing technique. And firstly, we are actually working with one of the key additive manufacturing vendor, EOS, right, to basically realize our oblique trapezoidal fin array structure, which is actually shown on the right. So besides actually realizing such novel fin structure, the additive manufacturing is actually very advantageous because it can actually realize what we call a unibody leakless design, right? So if you look at on the left, this shows a conventional cold plate design. So basically you have the fins that is actually fabricated on the base plate, right? Separately from the top cover, right? Yeah, but in order to sort of basically seal the cold plate, you need to actually either make use of mechanical sealing using bolts and nuts, as well as O-ring gasket, or you have to make use of a brazing process. So this will actually not only incur additional cost, time, but also the subjected to the possibility of leakage, right? Because most of the time the joints are not perfect, right? But associated with the use of additive manufacturing, we are able to basically print all the way from the base to the fin structure to the top cover, including the connectors, right, as shown in this top right figure, thereby actually allowing us to realize a leakless cold plate design, and thereby allowing us to address one of the key concerns associated with which is that of leakage. And what we did is actually then we integrate the cold plates into a 1U server, as shown over here. So this is actually a Mytech tie-in server comprising of 4 GPU and 1 CPU. So model of the CPU and GPU are actually provided here. So GPU is actually the NVIDIA GeForce RTX 2080, and the CPU is actually the AMD EPYC 7551T. So you look at the thermal design power for the CPU is about 180 watts, and for the case of the GPU card is actually each at 215 watts. So if you actually add up all 5 chips, right, so this 1U server is actually dissipating more than 1,000 watts, right, if it's actually air cooled. Okay, so after we actually integrated a cold plate into the servers, then we actually integrate into a standard 42U racks, right, as shown over here, right. Then in one of the configuration that we have tested, right, it actually also come with a active rear door heat exchanger, right, which actually allow us to discharge all the heat that we are able to pick up from liquid cooling into the hot aisle, thereby not having the need to, for example, lay piping connecting from a centralized coolant distribution unit to the liquid cool racks. Okay, so these are actually some pictures showing the test bedding that we are actually doing with a major co-location data center, right? So what we did is actually we have an air cool rack, a conventional air cool rack, right, using exact the same the servers, right, versus a liquid cool rack, right? Again, the same servers, except that we remove all the server fans and actually install or retrofit with our liquid cold plates, as shown over here, right? These are actually basically the quick connectors, dripless quick connectors that with a lot of easy coupling between the manifolds to the servers. So the next slide actually shows the comparison in terms of the server temperatures, right? So as mentioned, we're benchmarking liquid cool servers versus air cool servers. So you look at the air cool servers, right? So the temperature coding is such as the red is actually denoting elevated temperature in excess of, for example, 85 degrees Celsius, right? And the yellow temperature is actually ranging between, for example, 55 to 85, and below 55 will be green in color, right? So clearly the liquid cool servers are all operating at a much lower temperature compared to the air cool servers. But what's more important is actually what are the impact in terms of the energy in terms of the IT performance. Let me quickly show you that. So if you look at the figures on the left, right, it's actually showing you the average GPU comparison, right, between the air cool servers and the liquid cool servers. And at the bottom is actually the average the GPU temperature. So again, air cool versus liquid cool, right? So the red bars are actually pertaining to the air cool servers, and the blue bars are pertaining to the liquid cool server. So clearly, there's actually a very big drop in terms of both your CPU and GPU temperature. So maybe let's just use the GPU temperature as example. So if you compare 92.99 for a case of the air-cooled CPU versus a liquid-cooled CPU, you can see that the temperature actually dropped as much as for 40 degrees Celsius, very, very substantial, right? Then I think if you look at the GPU, it's actually slightly lower, but still of the order about 30 degrees Celsius reduction in terms of your chip temperatures. And once you're able to greatly lower your chip operating temperature, or what we call the chip junction temperature, right? You'll notice that your server power consumption or your chip power consumption actually dropped very substantially. So at 60% loading, we actually recorded 29% reduction in terms of server power, right? So meaning that besides the wonderful savings from your cooling system, right, you're now having this additional side benefit of significant IT power consumptions. So that's actually the like two advantages switching from conventional air cooling to high performance liquid cooling. And that's not all, right? So if you look at the clock speed, right? So we also measure the clock speed for the liquid cool versus the air cool servers, right? So if you look at the figure on the right, so for the case of the air cool servers, right? So the clock speed is actually fluctuating and at a much lower level, but you look at the average, it's actually around 1750 megahertz, right? Whereas for the case of the liquid cool servers, they are actually much higher, at almost 40% improvement in terms of the IT performance as measured by the clock speed. And you look at corresponding temperature, it's actually exactly what we have discussed in the earlier slides. So you can see that the temperature reduction in this case is actually as much as 45 to even close to 50 degrees Celsius. Again, showing that once you're able to very effectively manage your chip temperature, right? So you get all these wonderful side benefit of in terms of IT performance improvement, in terms of your IT power consumption reductions. And this slide actually shows the comparison in terms of the PUE. So I won't actually go into the details because I think we are probably running a bit short of time. But just quickly to highlight to you, right? For example, some of the PUE numbers, right? So the conventional air-cooled data centers is very quite efficient one, right? Having a PU about 1.4, right? But then if you look at our liquid cooling configuration, there are 3 of them, right? So some of the number actually in fact looks higher, right? So you see that in that case, then it doesn't make sense to sort of switch from air cooled to liquid cooling. But why is actually higher? Precisely because of the definition of PUE. If you look at PUE, it's actually defined as IT power plus facility power divided by IT power, right? So for liquid cooling, because the IT power actually reduces by, for example, 30%, right? So you actually get penalized, right? Because if your IT power, both in the numerator and denominator, is reduced by 30%, your PUE in fact will actually increase, right? But this is actually not to be frowned upon. In fact, this should be celebrated, right? Because besides the improvement or the reduction in the facility power, if you are able to also drop your IT power significantly, that in fact should be the very advantageous. So that's why we actually introduced this definition, which we call the effectiveness PUE, right? So basically it involves this E factor, which we define as the IT power from your air-cooled servers divided, by your liquid cool IT power divided by your air cool IT power, right? So for our case, since the liquid cooling is able to slash the IT power by the 30%, so this E value is actually 0.7, right? So basically, with this new definition, it actually allows you to very clearly make the comparison, right? So for example, if you look at 1.4 versus this most efficient configuration, which is chillerless, right? 0.77. So this will immediately tell you the energy savings or total power saving is actually 45%, okay? And if you also look at the water savings, right? So associated with the use of dry cooler, right? So the water saving can be as much as 98%. So again, demonstrating that the use of high performance liquid cooling can be very, very advantageous, not only in terms of power, carbon footprint, but also in terms of water savings. So basically, the key takeaways are actually summarized in these slides. So I hope that you have appreciated that through the use of very high performance liquid cooling, it can actually result in significant reductions in the power consumption in terms of both the cooling systems energy consumption as well as IT power consumption, right? And associate that obviously the corresponding reduction in terms of the carbon emission. I didn't quite show the details, but basically through the use of emission factor, you can actually calculate what is the associated carbon emission reduction. But in terms of percentage, it will be exactly the same, right? The second will be actually the single improvement in IT performance, as you actually shown just now, right? Close to 40% the improvement in terms of IT performance as measured by the clock speed. And last but not least will be actually the significant reduction in terms of water consumption, and especially for places like Singapore where we have a very shortage of fresh water resources, right? So if you can actually lead to a reduction of like 95 or even 98% in terms of water consumption, this will be very, very advantageous. So all in all, I think through the use of high performance liquid cooling, we can actually make the data center a lot more sustainable. So with that, I actually conclude my presentation. Yeah. So I think we should have time for a few questions.
Yeah, thank you, Professor Lee. I think with this, I will take up some of the questions that are posted under Q&A.
Sure.
So I think to begin with, Prashant Revankar is asking if you could please throw some light on circular sustainability practices in cooling design. If there is a substantial research effort in reducing or arresting heat generation at the chip level operation itself.
Okay. Circular design, it can come in different forms. So one is actually involving the waste heat reuse, right? Because as you mentioned, as we sort of gone through just now, right? So the heat that is actually being dissipated from the servers, in the case of liquid cooling, obviously will be actually drawn out by the liquid, right? So the usual way is actually to discharge this waste heat eventually through a cooling tower or a dry cooler. Right, then obviously that still contribute to urban heat island effects, whatnot, right? But if let's suppose you have a good end use, so imagine if your cooling tower is actually co-located with, for example, a laundry factory, right? Or in the case of temperate climate, right, whereby it actually embedded within a residential precinct, right? So with a recovered waste heat, then you can actually use it, for example, in the case of a laundry factory, you can use it to basically for the laundry purposes, or in the case of residential precinct, you can actually use it for space heating, right? So I think that's one way of where the circularity can be exploited for data center. The other way is, which is what I briefly alluded in the earlier slide, right? Whereby, for example, you can tap on the free cooling resource, right? For example, from the LNG regasification process, right? Because typically the cold energy from the LNG regasification is actually just wasted. It's actually dumped back to the sea, right? Instead of actually that, we can actually immerse, for example, a seawater exchanger into the flowing seawater stream, right? And instead of actually discharging the waste heat to the ambient, in this case, you can actually, in fact, make the seawater neutral, right? Because if you don't do anything, there's a certain delta T, right? Because you draw in seawater, go through an open rack vaporizer. So after coming out from the ORV, right, the seawater is actually a lower temperature, right? So if you don't control it and actually just discharge it back into the sea, that can actually harm your marine life. But if you are actually using the waste heat from data center, you can actually bring it back to neutral, right? Thereby actually making it more environmentally friendly and sustainable. Yeah. So I think there are really multiple ways whereby we'll be able to take full advantage of the circularity, the concept. But I think it's really requiring some master planning, right? For example, when maybe India's state government, when they're actually planning the location of data center, if they make a deliberate attempt to actually co-locate it with another industry that requires heating, I think that will be really very, very advantageous.
Okay, thank you, Professor. There is a question by Hina Ismail Sheikh. She's asking about the power consumption in oblique fins, which were shown to be lower compared to the straight fins. So she's asking, in the case of oblique fins, the mixing of fluid is taking place, so which means there will be an associated pressure drop, but still the power consumption is low. So our question is how?
Okay, yeah, that's an excellent question. So I didn't actually show the details, but if you refer to some of our publications, right? So I think associated with the flow bifurcation, right? So in fact, not only it actually reduce your thermal boundary layer thickness, it also reduces your hydrodynamic boundary layers, which from pressure drop point of view is not good, right? Because a thinner hydrodynamic boundary layer will translate to a higher pressure drop, typically, okay? But if you remember, right? So after the branching, right, the flow will eventually have to rejoin the adjacent channels, right? So there's actually, in fact, a flow recovery effect, right? So when we plot out the pressure locally, we notice as if while for the oblique channel, the so-called sections, right, you will actually, in fact, observe a bigger pressure drop. Okay, but immediately after that, right, just when it rejoins the adjacent channel, there's actually a flow recovery effect, which actually have a pressure recovery effect. So the net result is actually the overall pressure drop is actually more or less the same, right? So through optimization, basically, you can still ensure that the overall pressure drop stays at the same level while still achieving, for example, a 40, 50% or even 80% improvement in terms of your heat transfer. So I think that's where I think the optimization process is actually very important, right? You want to make sure that you don't necessarily incur a big trade-off in terms of a pressure drop penalty.
Okay, thank you again, Professor. Professor Dheeraj, do we have time for more questions or?
Sure. Yeah, I still have at least another 10 minutes. Yeah.
Okay.
Yeah, Professor, may I just have the answer for the second part of my question? Is there a substantial research effort in reducing the heat generation at the chip level? If you could quickly give me a...
Okay.
Yeah,
okay.
please.
No, certainly there is. So if you look at the chip development, right? So associated with the multi-core technology, in fact, there has been a pretty substantial reduction in terms of the chip power consumption. Yeah, so that certainly has taken place. I think easily about 10 years ago, if I remember correctly. But I think we are getting to a stage where, because of especially the related to the interest on AI, on machine learning, so heat is now coming back again, right? So I think for about 10 plus years or so, the heat density for chip has actually in fact dropped substantially. We are associated with the multi-core technology, but now it's starting to pick up again. If you look at some of the latest announcement by the chip makers, right, including NVIDIA, Intel, AMD, right? So their latest chips is already consuming anywhere between 400 to 600 watts. So that's actually very, very much higher compared to what we used about 2 years ago, right? If you recall that the slide that I've shown you, right? So the TDP that we had right, about 2 years ago is only about 200 watts. Now it's already close to 400 and going up to 500 and very likely 600, right? So you see while the chip development has been making progress, but at the same time, because of the increased functionality, right? So we are seeing that the heat is actually going to, or the power from the chip is going to increase again.
Thank you, Professor. So the next question is from Dheeraj Patil. We are seeing a good performance benefit due to the liquid-cooled servers. So is it also applicable to, let's say, cooling of solar photovoltaic panels?
Excellent question. So you'll find it interestingly, for a lot of application, even if it's actually so-called electronics, right? But even for solar, I think it's obviously a lot of electronics in these solar panels. So if you refer to my publication list, so one of our most cited paper, I think now is having a citation of about 700 plus. It's actually precisely on the active cooling of solar cells, right? And we have shown that if you are able to cool the solar cells efficiently, you are going to increase the efficiency quite substantially, right? Because especially for a lot of the solar cell or solar panel manufacturers, right? So when they report their efficiency, is actually done in a lab-based environment. So firstly, what they did is actually they immersed the solar panel in a cold water bath of 25 degrees Celsius. But then if you were to bring the solar panel to field, right, for example, under the sunny conditions of Singapore, right, the actual condition is definitely not going to be 25 degrees, the sea chill water, right, where your actual ambient temperature can be, for example, 35 or even 40 or even 50 degrees Celsius. That's when you observe a very significant drop in terms of the actual conversion efficiency. So if we can actually figure out effective method of actually cooling solar cells, certainly that will actually help to increase the conversion efficiency.
Thank you, Professor. Are there results based on the present results? Are they based on a particular liquid, or can any liquid show similar results in performance?
If you look at the various heat transfer fluid, water is still by far one of the most efficient, or the most efficient, probably the maybe minus more exotic fluid like the mercury or whatever, right? But water is by far the one of the most efficient heat transfer fluid, right? But then when you are doing liquid cooling, right, for data centers, some of the operators and their customers are very concerned because obviously the people still feel that the water and electronics do not mix, right? It can lead to short circuitry, can lead to damage to the IT equipment, whatnot, right? So if that's the concern, then you have to use a dielectric fluid. But switching to a dielectric fluid is definitely going to incur certain trade-off in terms of your cooling performance, right? On top of the cost implications, right? So that's why for us, I think why we focus on additive manufacturing, leakless design, right? Then in that case, if you can sort of eliminate concern related to leakage, right, then we will be hopefully able to still use water as the base fluid. But typically we add in certain glycol mixture, right, in order to address issues related to fouling, whatnot. Yeah, but water by far is still one of the most efficient fluid. So I always have this simple example, right? Water has been tried and tested billions of years, right? Anything else, right? There certainly be certain trade-off. Yeah.
Thank you again. I think this could be the last question. The previous question was from Sudhir Siddhapu Reddy, and this question is from Akshaya Tasin. This is about implementation of renewable energy in data centers and also the use of liquid cooling. So the question is it actually affordable? And if there are any studies or publications on it, kindly brief on it.
I think the integration of both high performance cooling solution together with green energy sources should definitely take place concurrently whenever possible, right? But in places like Singapore, where we have very limited land mass, so the integration of renewable then becomes quite challenging. Although I think the data center operators are also purchasing renewable energy credit or not. Yeah. So I think if possible, certainly I think it has to be a holistic approach, right, whereby you're not only focus on the energy efficiency improvement, but also look into bringing in renewable energy sources, right? So solar is one. The other actually is in time to come hydrogen or fuel cells for backup power generation. Yeah. So I think this is something that we are also actively looking at. So I didn't quite have a chance to mention, but here in Singapore, I'm leading a team to set up a sustainable tropical data center test bed, right, where we are actually working with major data center operators, right? So the starting on the various innovative cooling solutions, but we are now actually starting to also try to look into integrating with renewables. Yeah. I think specifically fuel cells. Yeah. You're muted.
Hello, Professor Kirti.
Okay, I just realized my mic was muted. I think with this we can conclude the session. We would like to heartily thank our esteemed guest, Professor Lee, for his invaluable time. We also thank the audience for their questions and for having an interactive discussion. On a quick note, to strengthen the inclusive technological innovation ecosystem in the areas of renewable energy, energy production, usage, and improvements in energy efficiencies, the Global Center of Excellence for Affordable and Clean Energy, that is GCOE ACE, IIT Dharwad, and Selco Foundation are looking for related problem statements. And the problem statements can be from sectors such as livelihood, agriculture, allied agricultural industries, resilient micro businesses, built environment, health, education, etc. And the submissions for the statement can be made through this Google form that I just posted here. And I think with this we can conclude the session. So thank you all for joining.
Thank you.
Thank you, Professor Lee.
Okay, sure. My pleasure. Thank you. Take care. Bye.
Thank you, sir. Thank you, sir.
Thank you.
Thank you, Dr. Dhiraj.
Thank you.
Thank you, professors. Thank you, Dr. Chair. Bye.
Thank you, Professor Kirti.
Okay, Dheeraj, I think we can log off. Okay.